Hey, have you ever thought how human actions are detected and classified in computer vision? Human actions such as walking with the dog, skiing, or even swinging cannot be described by one frame alone. So to tackle this problem, there are many architectures such as LSTMs, LRNs, transformers, and so on. In today's video, I am going to talk about the LSTM solution. Alright, but before we start diving deeper into LSTM architectures, long short term memory networks, it's important to talk a little bit about applications of human actions classifier. When we are talking about this product, this program, we would be able to apply it in security, in the detection of suspected actions, in medicine, mainly related to elderly care, detection of falls, and in robotics. Mainly if I want to, for example, a robot to respond appropriately to a human action. So now talking about long short-term memory networks, we have to dig deeper into the cell. In other words, the smallest unit of its architecture. There we have properties that allows to keep memory from previous state. That's why the name of the network it's long short-term memory. We got to have a lot of information from previous state. So we have the forget gate to discard useless information, and then the input gate where you got all the new information and aggregate to the network, and the output, which passes mainly the current state, which memory will be passed to the next stage, and also the output of this cell. The output can be, for example, a provision, a prediction, and so on. So CT means the memory of the last state, HT means the output of the current state, and XT the input. It's also valid to highlight that CT minus 1 and HT minus 1 is always related to the memory and information that comes from the network last states. So it will have all the information that is judged to be useful for making a provision in a time series based network. With that said, we can finally start coding. So right now I just opened my VS Code, the tool that I loved using for coding, and I will start opening the module that I had created. So right now we have here the class that I had programmed. It consists of a lot of libraries used, mainly focused in TensorFlow, that will be the backbone to all of this application. CV2 for analysis and image processing, NumPy for operations using metrics, tensors, and so on. And the yeah, and the sklearn because we will need it to split the quantity of frames that will go to test, validation, and finally training. Just a thing before we start is that here there are some warnings, but don't care about it because it's working, and it's just because of some configurations of the VS Code that I haven't done. However, it will still continues working. So in classifier model, that it's the class that I had created, we have a few functions, but essentially what they will do is like create a data set and then extract frames, features, assemble an architecture mainly with convolve, LSTM, max boolean when you want to extract and summarize characteristics from a bigger picture to a smaller one, time distributed, and a dropout. A dropout, what is dropout? Dropout is when you want to take away some part of the inputs to avoid overfitting throughout a network. Also, we will have in the final the flatten because we need to transform all these vectors and metrics in a column in a vector, and then the dense layer where all the previous layers will be connected. It's important to explain that here we will have the activation function called softmax because it's a classifier. So every time that you try to do a classifier, you will be using in the last layer softmax because it's a statistic distribution throughout all the probabilities. So you will be able to assess which class the video is most likely to belong to. Here we also have the predict function where it takes as an argument the video file path and then will extract its characteristics, append to a queue, and then will make predictions. The predictions will be occurring with TensorFlow as said before, and the class will be attributed. Bef After that, then the video will be subscribed with the label. So later I will show how does it work. Here we have the train step where we have the validation, we have the patience equal 10, the validation split, we have the process of restoring the best weight. So throughout the process, every time the best weight will be restored, which is interesting because it doesn't mean that if you add epochs, you will have a slight improvement on your network. Sometimes it even get worse. It was even a trouble that I had to face because after 30 epochs, the all the networks started to go worse and worse, declining and so on. So we have also here the evaluate function, where we got all the data that we trained and then saves in a JSON file. Also load model if we want to get our architecture and save architecture image where we have exactly the diagram of how our architecture was structured, save model, and then save metrics. So with that explained, we can finally go to our training.py where we start instantiating the class with the name of the dataset and then the list of classes. We then assemble our architecture, create the dataset, start training, and after that we save the module. So it's pretty simple because the module does all of the hard work. So if you want to use that, it's easily done. Talking about testing, we can go to main.py where we start declaring and instantiating the object. We load the model and then we use the predict function. It's also important to say that throughout this code, we make the assemble, we make a capture that has the comparison between the original and the predicted video. So if I execute right now, like that, we will be able to see oh, right, sorry, I forgot to activate the virtual environment. So activating right now and then the same command again. We will be able to see some warnings, but it's totally normal because it's just some warnings regarding TensorFlow configurations. And then we will start to preview and predict some videos. So let's just wait a little. Yeah, after that accelerated time the speed up that I've done, we can see right now that it's predicting. And after a while, we will be able to see an output video. So right now we have here the comparison before and after the classifier. But as I trained the network, I started to think which quantity of frames will give the most performant state regarding videos long enough as 10 seconds. And then I started altering its parameters. So firstly, we have the accuracy graphic where we can see a comparison between 45, 60, 75, and 90 frames. And we realized that here 60 is the one that is more performant, more efficient overall. The same goes for recall, the loss, and the precision. It's interesting also to note that 90 frames are also a good performance if we compare to the optimization and the behavior of 60 frames. Particularly, it's also important to highlight that those results are incredibly and enormously influenced by the duration of the video. So if you want to identify accurately some larger video, you might require a bigger quantity of frames. In this case, the UCF50 is a dataset that has short videos and also has low resolution. So in this context, particularly, its performance is better when we got to use 60 frames. So the conclusion is that this study has demonstrated that LSTMs are a good way to solve human classifiers problem, mainly regarding videos. And it's interesting to develop a further study regarding not only LSTMs, but aligning this technology with a lot of other ones, such as continuous learning for not need the implementation and the retraining throughout the process. If I want to add, for example, just one class, the user terminal, because sometimes code is so abstract, so it's difficult for people who are not familiar with using TensorFlow, and testing different architectures, because sometimes increasing the number of layers, altering the activation function, how the LSTM is structured, we could achieve a better performance. Here we also have the developer team that is made by me, Marcos Aurélio, and my academic advisor, Elton Maia. And this work was made for computer vision subject in the Science and Technology School of UFRN. Thank you, and if you have any doubts, please just email me, send me a message on LinkedIn, or send me a contact via GitHub. Thank you. See you.